I think one of the biggest challenges is how to compute phi given f. I think it just takes it takes a conceptual twist at the end to be able to get this right. One way to do it is keep in mind that f dot dr is a total derivative, and so you can use any path. So you could, in principle, just pick a path that's convenient, do that integral, and you'll get phi. And that's what the book shows you, that's what Boas shows you as a method to do it. I actually find that one not as satisfying. And so what I want to show you is kind of a standard way. I've learned it, and I see most physicists do it. And the trick to it, is just keeping track of what you get when you integrate so that you do not duplicate yourself. And so I think the easiest way to do it is with a concrete, specific example. And what does it mean for this function to be the gradient of phi? Well, it simply means, right, if you remember what the gradient is, that this is d phi dx, this is d phi dy, and this is d phi dz. So I can now do each of these integrals. But what I have to keep in mind is if this is a partial derivative, so if I normally integrate, if I integrate f with respect to x, what do I get if I'm doing the indefinite integral? I get something plus a constant. So if I do an indefinite integral of phi, which is a function of x, y, and z, with respect to x, what am I going to get to add at the end?
A constant that's possibly a function of the other one.
So any function of y and z, I can add to this integration, because df dx will make that 0. And that's the key step. So let's just write out each of these. Normally I would take the time to ask you what they are, but I'm just going to write them out. And then let's gather terms. So if I take the d phi dx equals 2x minus y, 2x times y minus z cubed, I'm going to get x squared y minus z cubed x plus my function 1 of y and z. So integrating with respect to x of this gives me x squared y. This is a constant relative to x, so I just get minus z cubed x. And then I have my function of y and z. If I do this with respect to df dy, that's equal to x squared. Notice I just get x squared y plus some other function, this time of x and z. And with respect to z, I have it equal to minus 3xz squared plus 1. So I'm going to get z cubed x minus z plus f3 of xy. Those are my three integrations. Now, the thing is, this function of x and y has to be contained in my other integrations. This has to be contained in my other integrations. The other one has to be contained in my other integrations. There's no other things of x and y that can show up. So the terms here that aren't written as f's are everything that this could possibly be. And I just have to be careful not to double count. That is the mistake people make at this point. Okay, they do this and then they double count. So let's just line these up. Okay, my three answers for phi. My first answer for phi came out x squared y minus z cubed x plus some function that's only y and z. My next answer for phi, I look at it, it also has an x squared y, so let's just write it under there. And it has some function that just depends on x and z. Well, here's a function that just depends on x and z, so let's put it there. My final phi does not have an x squared or a y, but it has a function that just depends on x and y. So let's put it there, because that is a function that just depends on x and y. It has a z cubed x, and it has a z, which lines up with a function that depends just on y and z. This could also be counted as a function that depended just on x and z, but I already had one of those. So this takes care of that f, this takes care of that f, and this takes care of that f, and now I make sure I don't double count that or double count that, and I'm going to write phi of x, y, z as minus, I'm sorry, those were just x squared y's, as x squared y minus z cubed x minus z. Now I could, if I wanted, add a constant to this. Just like in physics, the potential energy, the exact zero doesn't matter, right? Because I do have an overall constant still. Very rarely do we write that. If I ask you for the potential and you didn't write that, I wouldn't mark it wrong. It's just something that very rarely comes in. But this is the key, and this is the piece. So the partial integration part, I think everybody usually does when I have this class or I teach and people do it. What they don't then do is handle those functions and keeping track of things correctly. So that's why I think this example is very useful. And you really want to see what I did here at the end to just pull out these terms. Notice there's no 2's here. I didn't add things up, okay, because that would mess up my things. You can always check. Take the derivatives of these and make sure it works. If you double counted, those 2's would show up pretty quickly. You'd get the wrong answer. So hopefully this example makes it all work.